start our session of electronics. And time limit for each presentation is 15 minutes total time. So please fit in time, maybe 12 or 13 minutes for presentation and 3 minutes for questions, okay? And we have first presenter from Poland. I think he present himself, and the topic is temperature influence analysis on the selected current sources stability in the static and dynamic operating states.
Can we start?
Yes.
Okay, thank you. My name is Wojciech Walędziuk. It's quite not so easy to pronounce name and surname. So I will talk a few words about analysis of temperature on current sources. So my presentation, firstly I will start with some introduction, then I will say a few words about tested current sources. Oops, sorry. Next I will say about something about laboratory stand and research procedure and achieved results. So the goal of our research was to analyze the temperature influence on current sources. We have chosen only 4 types of well-known circuits. The first test consisted in changing temperature versus load, changing of load for current sources. The other test was related in transient state analysis and during switching on and off current sources to the circuit. I think everyone knows different circuits which can be used for resistance measurement. You can see here, for example, well-known Weston bridge. We can also measure resistance with the use of direct measurement with the use of current sources built in meters. We are measuring in such cases voltage drop of the resistance. We can use Anderson loop. We have here a simplified version without subtractors of this kind of measuring circuit, and we in general working on a different kind of signal conditioner, which name is two current source bridge. We have here 2 current sources built in the bridge, and thanks to that circuit we can measure 2 quantities at the same time. Of course we have to do some calculation. Here we have an example of 2 current bridge in which we have applied 2 current sources which should have identical parameters of electrical parameters. The temperature stability of this current sources is also crucial when we want to apply such kind of bridge in industrial applications. Of course, the circuit can work when the current sources are not equal, but the formulas for calculating these values of resistance, for example in strain-gauge system, or with the use, for example, temperature sensors such as platinum sensors, these formulas are more complicated in order to express its values. Next version of our current source, double current source bridge is a bridge with some keys built in the system. In this system, the source current source properties are important if we take into consideration dynamic processes, such as switching on and off current source to the bridge. The slower, for example, response, the slower time of the response of the source settling time The smallest frequency of switching this in this bridge keys can be applied. Taking into consideration presented current sources limitation, if we take into consideration static and dynamic processes, we took a decision of doing some research in which we analyzed thermal properties of in a dynamic and a static states. In the research we used 4 well-known devices, maybe not exactly devices, such as by structures of the current sources. First was a well-known LM317 element. The next was linear technology current source. Third was and fourth was a MOSFET transistor-based current sources. Laboratory stand. In this slide we can see printed circuit board of on which we placed several current sources. For, as I told you before, for purpose of this research we used only 4 of current sources. Laboratory stand. We have used climatic chamber as an environment for our device. Also, we used thanks to this chamber, we can we had a possibility to steer the temperature inside and humidity. What is more, we use programmable electronic load and 2 multimeters, 6.5 digit multimeters. All of devices was connected to the PC computer, which and all of the process was steered with the use of LabVIEW system. The first research was the temperature distribution analysis. As you see in this research, we achieved almost regular distribution of the temperature. This means that there are not additional thermal factors which could be a source of error in our research. As you see, we have some spots. It's lighting emitting diodes, but this part of the circuit does not significantly affect the research results. Here we have an example of a dialog window of our virtual instrument, which was written in a LabVIEW language, G language. Thanks to that, we have a possibility to collect our data during research. In this slide, we can see simplified version of our state machine, which was used in our research, in our program. In the first thread, we steered climatic chamber. Also, we have measured some temperature inside. What is more, the second thread was responsible for sending command to the resistance load, and the third was responsible for reading data from the multimeters. Research results. Maybe firstly about some procedure of measurement. We have chosen the temperatures range between -5 degrees Celsius to 70 degrees Celsius with a step of 5 degrees of Celsius for measurement this source. the temperature, when the temperature was stabilized, we achieved, for example, 5 measurements for 1 point for characteristic. After that, we can have a possibility to calculate uncertainties of type A and B, and of course combined uncertainties for measurement at that point. After that, we increased the values of resistance load of 5 ohms up to 400 ohms, and so on and so on. What we can see, there is not big influence of the temperature on the stabilized current for current sources. For all analyzed circuits, we will see after. Maybe I will change the current source. In order to see more precisely values of the measurements, we apply differences between specified temperature which was related to the 0 degrees characteristic. As you see here, there are small points like here. It's a source of error which takes from the resistance load. Yes, it's a kind of it's a place when here and here, for example, when the resistance load changed the range inside, the circuit, inside the resistance load. It's not so good. What is more, maybe it's information for you how many we have to accomplish measurements during one measurement process. We have to do 3,070 measurements during whole measurement process for one series of characteristics for one current source. Here we can see that the characteristics of difference between in relation to the 0 degree. As you see, the differences are not big, and in the stabilized part of the characteristic, it's a source of errors I have told you before. This part of characteristic is not important in a practical application. That is why we can. It's not necessary to take it into consideration. Okay, for linear technology, it's adjustable current source, and for MOSFET transistors, as you see, errors are bigger than in previous types of current sources. Second test we did during switching on and off current source to the measurement circuit. The test was accomplished in the temperatures of -5 degrees of Celsius and for 70 degrees of Celsius. The load resistance was 100 ohms, and we switched on and off 10 times current source during one research. Okay. As you see here, the smallest difference between rising and falling time occur for MOSFET N-type transistor, but huge settling time values around 1 second and rising time about 0.5 seconds are disadvantage of this current source. For our application, linear technology current source was the best choice. If we take into consideration smallest of course, and rising and falling times, and what is more, settling time for different temperatures. Okay, summarize. The current sources based on the integrated current sources was the best solution, optimal solution in our application. If we take into consideration dynamic states and of course static states, and what is more, MOSFET-based transistors were more stable in terms of temperature, but the time of around 1 second eliminates this solution in our bridge with the keys when we need to switch it on and off during research. That's all. And in next maybe in the future we will take into consideration only linear technology current source, maybe something like which is quite the same. We will take into consideration quite the same current sources which are integrated. That's all. Thank you very much.
Thank you. So do we have questions?
This is analysis, so as a scientist you know how does it work. What will be your solutions as engineer to compensate these problems? Do you have it? Because you know, as scientist you want to know. As engineer you want to solve a problem. How you will solve the problem?
The best thing is to use integrated circuits, not circuits based on the different elements placed on the PCB boards. It's
some compensation,
maybe some compensation. Maybe we can use some, I would say, separation, thermal separation for current sources on which are placed on the PCB board. Because sometimes when you apply some supply to the circuit, this element can hit the PCB board. That is why we have to use some separation, thermal separation. That's a solution, I think.
Some questions? Thank you. So we not fit in time on first presentation. Maybe we will reduce some other. We have presented from China, yes. And the topic is hardware in the implementation of single iterated multiplicative inverse square root.
Okay, thank you, Chairman. Okay, ladies and gentlemen, good afternoon. Okay, we are going to today. I'm going to talk about the implementation. It means about traditionally we implement algorithms in software to do some process, and our project is focused on the inverse square root. This is the schedule. And first, we were talking about the motivation and the development of some of the references. And second, we will analysis the different approximating methods of to implement the inverse square root. And finally, we will implement this method in hardware and doing some comparisons. And finally, we will show an application. Progress in digital signal and integrated circuit technologies. We have many arithmetic element functions such as reciprocal, square root, and square root reciprocal. This project we will mainly focus on inverse square root. And as the development of real-time processing and acceleration of some complex algorithms is very necessary. So we have to find a trade-off between among these high procedure and maybe high throughput and with no cost. So the challenges is that how to build competitive solutions for these arithmetic element functions. And this is an example. We in the Cholesky decomposition, we implement in software. It will take up to more than 6 microseconds. So it's a long time. If we apply it in real time in application, such as in real time processing, so it's very slow. So we have to find some ways to accelerate. And there are some methods in realize inverse square root, such as table techniques and subtractive techniques and multiplicative techniques. The limitations of each method is very there are limitations such as cost and non-latency. Maybe the speed is very slow. This picture shows the some of the reference, the roadmap of the reference, and so the three techniques: table and subtractive and multiplicative. And we have made used some of the recently developed technologies. In the initial seed, we used multiple piecewise linear approximation, and we used quadratic convergence, Lithuania method, and also we, in order to reduce the multiplier, we used the multiple constant multiplication. Okay, let's go to other methods. In the there are, I just have thought there are several methods to implement the inverse square root. So we choose the combination of some of the techniques. This is the first is the initial seed. We use these equations. Use these equations to implement the initial seed. We use the three piecewise linear approximation. And we use Lithuania method to to compute the result of the inverse square root. And this is the derivation of the Lithuania method. Okay, this picture shows the comparison of different methods, the procedure. We have compared 5 methods, and just as shown here. 8 piecewise linear approximation in highly nonlinear range, and first order, and single Lithuania method, and the table techniques plus multiplicative method. We have compared the different memory bits. And M4 is the 3 piecewise linear approximation with single Lithuania method, and M5 is the 4 piecewise linear approximation. We can see the average error different method has obtained. This shows the M1 to M5, and we can show the relative average error. Different methods has occurred. Finally, we will go to the hardware implementation. In our project, we have used this technology, a multiple constant multiplication, which means to reduce the hardware cost by eliminating some multipliers. This means use additions and shifts to implement multiplication. We have used a project developed by some researchers. Okay, this is the hardware architecture, which means this is CSE is MCM, and we also use this part to get the initial seed, and they use Lithuania method to get the result, to compute the result. This table lists the performance comparisons of different methods. As I have just mentioned, we considered five methods in this part, and we implement all these methods in hardware and compare different cost, performance, and latency. We can see that Tempo has a competitive solution for many applications. Second, we have used these different architectures to in Cholesky decomposition. We have implemented different Cholesky decomposition and used the hardware architecture we have developed to compare the performance it has obtained. This structure used is a table. It's a table techniques. And this one we use the MCM techniques. And this is the proposed M4. We use 3-piecewise linear approximation with a single Newton-Raphson method. We also in this part we also use the MCM techniques. And this is the 9-order Cholesky decomposition. The result is listed here, and we can see that from this table we can see that when you use MCM techniques, it can have a performance improvement. Also, this one is improvement, yes. And let's come back to the first example we have showed. In Cholesky decomposition, we use the software and we use the hardware. The time it cost to process type line order 9. You can see that there is a huge speed up. Okay, the conclusion is that we use the combinations of the existing techniques, such as these ones, to yield a good performance trade-off for inverse square root, and the technique of MCM can effectively improve the hardware performance in terms of speed and throughput. Thank you.
If I understand good, you implement that in fixed point. Is it possible to implement your solution in floating point?
Floating.
The solution is okay. We have compared different architectures, and it's a trade-off. It's a trade-off to implement different methods. So it's hard to say which one is the best, and it depends on your application. And we have used our proposed architecture in image processing, in compressed imaging. We use the table techniques and plus multiplicative techniques. So it's hard to say which one is the best. It depends your application, but in our research we found that if you use multiple constant multiplication, it can improve the performance, maybe or not. Okay.
Can you name some real-life applications that your technique can be used? In what kind of applications?
We have used in compressed imaging.
Video processing or what?
What?
Real-life application. What is the purpose of your technique? For what kind of applications?
Yeah, it's like this. We are developing compressed sensing the algorithm. We want to implement it in hardware also. So we find that there are a lot of data to process, and we will use inverse square root. So we focus on the inverse square root or not, and compare different architectures.
Okay, thank you. No more questions? Thank you. So the next presenter will be from Lithuania, Navikas, and the topic is design and optimization of pulse magnetic field generator for cell magnetopermeabilization.
Hello. So as you can see from the topic, our group is focused on bioelectronics, and to be more precise, we are focused on biomedical electronics to have biological applications to treat cancer cells, tumors, etc. So, first, the motivation. So, one of the most known, let's say, biomedical techniques to use pulsed electric fields or pulsed power electronics is electroporation. So, the purpose of electroporation is to apply high pulsed electric field in order to induce sufficient enough transmembrane potential and permeabilize a cell. You could destroy a cell, you could increase the permeability to alpha molecules, drugs, to DNA. But the straightforward disadvantage that usually in electroporation you need electrodes in order to generate high pulsed electric field. And as a rule, these techniques are invasive. So you need to penetrate the tumor, generate the sequence of pulses, create some kind of protocol, and then you have permeabilization, reduction of tumor growth, etc. The method is economically good, wide solution. It has high applications in medicine. It's already made its way to clinical applications. So you could transfer drugs, genes, you could treat the tumor, you could increase the wound healing, and you could also apply this method in activation or sterilization of food process, in food products. But our group decided that we could, let's say, try or research or alternative method where you could reduce the disadvantages of electroporation, minimize them by application of pulsed magnetic fields. These are commercial devices like electroporators that could be, let's say, applied in both clinical research or in laboratory, and usually you need some kind of electrical pulse. With pulsed magnetic fields, we try to copy this, let's say, methodology. Therefore, we need to generate a pulse that should be well controlled. You could control the pulse duration, the pulse amplitude, the number, frequency of pulses, and as a result, observe the biological effects, the cause biological effects, both, let's say, in living microorganisms or in vitro, like you have a cuvette, some kind of sample, and just laboratory research. So we decided that we need high power systems, a device that can accumulate high amount of energy, and therefore discharge it controllably through an inductor. In our case, both the power generators and the inductors are self-made. They're developed specifically for each experiment, and each generator is in some kind is unique. But what you get with pulse power inductors, where you can generate pulse magnetic field, you don't need invasive techniques. You don't have electrodes, therefore you could treat the cells, you could treat the tissue non-contactlessly. As a result, potentially you could apply this method similar as an electroporation. So the parameters of our required generator that we want to have at this study. So our magnetic field should be like 4 to 6 Tesla. Based on preliminary data, we investigated and knew that these kind of magnetic fields, if they are fast enough, if they have high enough induced electric field component, they are good enough to induce significant detectable effects in biological cells. So as a result, our current should be in the range of 1 kiloampere. We limited our device to 2000 kilovolts, and that's based on the load calculation. And we tried to increase the flexibility of the generator. So we could control the pulse duration, the pulse number, the frequency, and our volume of effect right now is 10 microliters in this generator, because this generator was developed for in vitro studies, therefore for fundamental research of, let's say, magnetoporation technique, which is alternative or in addition to electroporation. So this is the simplified circuit of the generator. We used 4 MOSFETs, 2 in series, 2 in parallel. We have capacitors, one faster, one is more inductive, but as a result we have high power, high energy accumulation. The most significant part is the inductor. We need to develop the inductor specifically for each experiment. Therefore, we need to control the number of windings, the volume of effect, and therefore always control and observe the distribution of magnetic field. For transient process compensation, since we are using inductive load, we need snubber circuits, crowbar circuit, and we use a shunt resistor to have an overdamped circuit response. Therefore, our generator would generate some kind of similar to square wave pulse, which is advantageous for electroporation or, in this case, magnetoporation. So the development of inductor was made in COMSOL multiphysics environment. So based on this model, we analyzed the distribution of magnetic field, induced electric field, and therefore, if the results are applicable, if the results are acceptable, we can develop the actual prototype. The problem with our inductors and with all solenoids that if we can get let's say homogeneous magnetic field, the problem was that the induced electric field is not homogeneous. So in each experiment, when we have observed, let's say, a response of the cells, like the cancer cells or any or bacteria or any other cells, we need to account that the cell that was here experienced different effect than the one that was in the center. So the special distribution of cells in the suspension has an effect. And actually, right now, we have some kind of well-developed mechanism why it happens and how cells differently react both to magnetic field and to the induced electric field too. So basically we have 2 responses during one pulse. In this case, our generator was like up to 4 microhenries, and with the, let's say, 900 amperes, it could generate up to 6, something like that, Tesla. But this is a model data, simulation. We compensated the transient processes, so basically since our inductive load is dominating, we just compensated the overvoltages and induced voltages of the MOSFETs with RC circuits, and based on simulation data, and then experimentally just use the RC values that were found in the simulation. As a result, we are able to, let's say, have 2.4 kilovolts total commutating voltage of our, let's say, switches, but all the voltages were controlled, and we still had a reserve of 400 volts while the switches were successfully commutating. The measured pulse was like that. This is the influence of the compensation circuit. Obviously, we could go and make it a better square wave form, but the problem is that we have still risk if we use different inductor and we are constantly switching inductors. You could have a too high voltage, and our MOSFETs will just burn. So we have this kind of transient process during our, let's say, generation of the pulse. Applied research. So we use cells. This is control. Sadly, it's not so well seen here, but you could see that the cells are slightly fluorescent. So we used a fluorescent marker that is not usually going to the cells. If the cells are, let's say, having good cell integrity, so the membrane is quite good, but after application of pulse magnetic field, after using of this generator, we can see slight fluorescence of the cells. Obviously, when we apply electroporation, so we use electrodes, we put the cells into the cuvette and apply electrical pulses, we see better fluorescence. Right now, all the available studies on magnetic operation show weaker efficacy of magnetic field. But the proof of concept has been already confirmed by independent groups in the world, and it's agreed that pulse magnetic field could be effectively used to actually permeabilize biological cells. And these types of pulse magnetic field generators are in high demand, because if you can buy an electroporator, there is no way you can buy a pulse magnetic field generator with the parameters that are required to actually permeabilize a cell. Usually magnetic field generators are like for stimulating of tissue, like transcranial magnetic stimulation or something like that. Our future prospects is to actually use this methodology in vivo. Right now we have a project. In this case you can see electrodes, so that's conventional electroporation, but we always need a reference. Since there is already a methodology that's, let's say, present on the market for 20 years, we always need to compare our new proposed methodology with magnetic fields with the clinically acceptable and right now popular electroporation techniques. In our case, we use planar inductors that allow contactless treatment of mice, of the surface, and hopefully will be successful. Thank you.
Thank you. So, questions, please? Ben?
How the efficiency of magnet operation compares to son operation?
It's weaker. I mean, right now, if you have, let's say, mammalian cells, you could permeabilize with the available protocols of our, let's say, our protocols, like 30% of permeabilization. If we use, let's say, high amount of pulses, so the sequence is getting longer, but then we should account for gel hitting. With collaboration of groups from the European Union, from Slovenia, we were able to get 80% of self-permeabilization. But the problem is, with, let's say, with son operation or electroporation, you have a better molecular transfer. With magnetic fields, right now, the best we could offer, or any group that's working in this field can offer, that you have high permeabilization, but the transfer is really weak. Something similar is observed with nanosecond electroporation. So you can successfully permeabilize the cells, but it's hard to inject molecules inside. With magnetic fields, it's something similar. We're already speculating about the electrophoretic forces that are induced in the suspension during our treatment. But right now, magnetic operation is weaker than son operation.
But you never evaluate the percentage of permeated cells per joule.
No, that's typical for food processing.
In such case, it would be even less.
It's less.
What confuses me, can you go to your electrical circuit?
Sure.
Yes. Okay. What is the capacitance, total capacitance of C1 plus C2?
C2 is several microfarads, C1 is higher. So C1 is to actually to give energy to have high dBdt, and C2 is just to have the, let's say, like a filter.
Because according to the parameters that you have given, you need from 1 to 10 joule. So where they are coming from?
1 to 10, actually in the paper there is exact number of joules we have calculated. Have you multiplied by the microseconds?
I have multiplied by inductance, because the energy you need to excite can be calculated by current squared times inductance. Of course, it can be multiplied by time.
Mm-hmm.
The current by time, but
I mean, we have a shunting resistance to have an orthodynamic response, and this is actually an experimental pulse that is measured with the needle.
But anyway, it is experimental results, and
yes,
you have the confirmation that you
yes,
have reached.
Yes.
Thank you. Thank you. Question. Thank you. So next presenter will be from Turkey, and the topic is novel first order current mode MOSI phase shifters.
Okay, my name is Emre Arslan, I'm from Turkey. I will present my paper, which is about novel first order current mode MOSFET phase shifters or all-pass filters. I will start with a small brief introduction, and then I will show you the proposed phase shifters, and then I will talk about the design algorithm very shortly, and then I will give the simulation results and conclude the presentation. MOS only stands for metal oxide semiconductor implementations. It only uses the MOS transistor and its parasitics. As all you know, if you want to design, for example, a filter circuit, you need resistors, capacitors, but MOSFET has some parasitic capacitances. For example, if it operates in saturation region, the gate to source capacitance is dominant. So the original idea stems from this point. Can I use this parasitic capacitance as a physical capacitance? Plus, it also has a GM value, a transconductance. 1 over GM makes a resistance, so can I use this as a physical resistance? This is for MOS only, but if you use a physical capacitance instead of a CGS value, for example, then this is called MOS-C or maybe GMC filter design. What is advantageous about this design is the low cost, low power, and also small chip area, because you only use the transistor itself. It only operates in high frequency ranges because you have very small capacitance values in femtofarad range. So the pole and zero frequencies are in very high frequency range. Okay, we use the parasitic capacitances and the GM value of the MOSFET as external capacitance and external resistance values. This table shows some filter circuits from the literature. They are first order all-pass filter circuits which use some active circuits. For example, current conveyors, current difference and transconductance amplifiers, and some active circuits. And these are the number of the passive elements that they use. They use capacitances, 2 resistors, for example, for this one. It includes 32 MOS transistors, and this is the layout area and the power consumption. But these two ones that we proposed here use only MOS-only circuits. We use capacitors here because I will show in a little bit later that we have to guarantee the transfer function of the first order filter circuit. We prefer to use MOS-C filter design in this paper. As you can see, in total, the core circuit plus the biasing circuit only consists 8 MOS transistors. And this is the layout area, as you can see. It is the smallest one, and the power consumption. These are the proposed first order phase shifter circuits. These are the core circuits. These are the AC implementations. They only include the core circuit. There are no biasing transistors around, as you can see. For example, the gate of this is connected to the gate of this one and the drain of this one, so there is no DC current flow here. This is only the core circuit, this is only the AC implementation. And this is NMOS implementation, this is the PMOS implementation. They are two different phase shifter circuits. And these are the transfer functions. As you can see, we prefer to use a physical capacitance here. This is for the NMOS implementation, and this capacitance is for the PMOS implementation. By connecting this, the drain current of this transistor give me an all-pass filter transfer function, this one. And the drain current of this transistor over the input current also gives me another all-pass filter transfer function. These two are core circuit plus the biasing transistors. These 3 transistors are the core circuits, and another transistors around are for DC biasing purposes. This is the total implementation. It only consists 8 MOS transistors, so it have a very simple structure. If you prefer to use this one, this is the load resistance. It must be connected between the drain of this transistor and between the DC power supply, VDD. If you prefer to use this one, the only difference is this. You can use a grounded resistor as a load. And for MOS-only design, if you take into account the CGS values of all the transistors like this, you will have a complicated transfer function like this. But if I assume that the physical capacitance that I connected is much more greater than the gate to source capacitance, and also if I can assume this equation, this reduces to the easiest transfer function like this. After these assumptions, the transfer function looks like this. So it's a first order all-pass filter. And these are the transistor dimensions of the phase shifters. They are obtained from the design automation tool that I will talk about in a few minutes. The width and length of the transistors are all obtained from using the design automation tool. How does this design algorithm work? I have some specs. For example, the center frequency, the Q value of the filter circuit, the gain, the input impedance, and also the output impedance. I take these ones as inputs, and I generate the bias currents, bias voltages, and aspect ratios of the transistors. These are my inputs, and these are the outputs. First, we start with using mathematical software tool. We model the transistor as a voltage-controlled current source. As you know, the small signal model of the MOS transistor is a GM times VGS current source plus the capacitance, the parasitic capacitance between gate and source, CGS. It's a 3-port device, and in each case, we randomly connect the MOS transistors. And in each case, we also generate the transfer function. If the transfer function gives me a first order filter circuit, then I select this one. It's a candidate. I again rerun the circuit, the software, and it regenerates another topology which is randomly connected. And if the transfer function gives me another first order filter circuit, I also use this one. It's another candidate. Then I generate the netlist of these candidate circuits. After the netlist generation, I use another MATLAB script. This MATLAB script takes my inputs or the user specs and then generates the aspect ratios, the bias currents, and bias voltages. These are the specs of user specs: power, area, center frequency, the Q value. And then the design automation tool generates me all the physical quantities, the aspect ratios, bias voltages, bias currents. These are the values of the simulation results, the supply voltages, and these are the simulation and calculation results. Measurement results are obtained from the SPICE simulations, and calculation results are obtained from the design automation outputs. As you can see, they are very close to each other. These are the simulation results, gain and phase responses. As you can see, the gain changes from 180 to 0, and 0 to 180, because one of them is an inverting type, first order all-pass filter circuit. What is good about this circuit is you can change the pole frequency by changing the biasing voltage. For example, the pole frequency is easily controlled by the bias voltage from between 7 megahertz and 11 megahertz. So it's possible to change the center frequency by only changing the biasing voltage. Time domain simulation results. For 10 microampere peak-to-peak input value, we only have 1% total harmonic distortion for NMOS implementation and 3.6% total harmonic distortion for the PMOS implementation. These are the corner analysis for small, fast, and typical transistors that we use. As you know, they are the even corners. And these are the simulation results for these 3 different transistor models. And finally, Monte Carlo simulation results. We changed the value of the capacitor, the physical capacitor that we connect, and also we take into account the transistor mismatch values. To conclude, we use Mathematica, MATLAB, and also LT-SPICE to start, we start from modeling the transistor as a 3-terminal device, randomly connected them, generating the transfer function. If it is candidate, we use MATLAB script to generate the outputs using the user specs, input values. Then we make some LT-SPICE simulations and want to see that if the candidates are working properly or not. These softwares or the scripts can also be used for MOS-only design, not only for MOS-C or GMC, but we also use or propose some MOS-only filter circuits using these scripts. Okay, this is the end of my presentation.
Thank you.
Thank you.
Questions, please?
The capacitor that you are simulating, it is nonlinear?
It's a linear
Is it
capacitor.
parametric?
It's a 5 picofarad capacitor. Yeah.
Is it parametric?
No.
What makes you think so?
By doing simulations,
No, no.
We-
What makes you think? Because I would expect CMOS
Uh-huh.
gate capacitor to be nonlinear.
yes.
What makes you think that it is linear? It is non-parametric and linear. Why are you making this assumption?
We obtain the transfer functions. The transfer function says me this CGS capacitance must be much more greater than the other two. So there are 2 ways. The first way is to make this transistor very large, and the second way is to connect a physical capacitor to these floating capacitor to these points. So we prefer the second one. If you make this transistor very large when compared to other transistors, so you can also obtain this transfer function.
Okay, thank you.
More questions? No? Okay, thank you. So, we have one more presentation from Poland. The topic is electromagnetic compatibility of impedance source inverters.
Thank you very much. My name is Krzysztof Bernacki. I come from Silesia University of Technology, and today I want to say something about electromagnetic compatibility of impedance source inverters. First of all, I say something about impedance source network and difference between impedance source network and the impedance source inverters. Then something about motivation. Then answer investigation, results, and a few words about conclusions. Okay, what is it? Impedance source network. It is a new DC-DC converter, and why I said that this is new? Because first article is proposed for Professor Peng and called Z-source inverter in 2002 and 2003. Is this two article? What is different between impedance source network and the impedance source inverter? Because impedance source network is only structured DC-DC converter, and this converter can working with voltage source inverter or current source inverter. So if we connect impedance source network, this is the fundamental structure, Z-source inverter. If we connect the Z-source inverter with, for example, voltage source inverter, we have a impedance source inverter. Okay. How impedance source network working? In all impedance networks, the energy is stored in the inductance in the shoot-through state, which is implemented by switches in the half-bridge inverter. It's zero state. Zero state is the time when the input voltage of the output filter LFC is zero. Of course, now we have, for example, now we have 30 different impedance source networks. If somebody wants to know something more about structure, please find this information in Professor Peng publication. It's very good one's publication. Another structure is, for example, quasi Z source, cascade quasi Z source, LCCCT quasi Z source, and for example, delta Z source. Okay. In our research, we use only constant boost control. Is the basic method to control impedance source network. This solution characterizes this the coefficient dz is shoots through state is constant. Why we choose this one? Because we want to analyze only influence to structure and don't analyze additional influence. And of course, many another methods you can find in another very good publication is Professor Peng is second part review of control and modulation techniques. The author of structure presents disadvantages and the advantages his solution. They describe solution dedicated to reduce problem with electromagnetic compatibility. However, in the literature, no one has performed comparative studies to several structure. So, in novelty in this research, in this paper, is present the results of the research on conductive disturbance and radiated emission to 5 selected with us impedance source network. This compare were performed in certificate AMC chamber along with a discussion in these results. Okay. Compare 5 structure. Yes, why this one? Because this is the first structure. This is the most simpler. As we can see, they have two capacitors, 2 inductor, and 1 diode. This is the Z source. This idea belongs to Professor Peng. This one is a quasi Z source. It's the similar. Is only one change because this diode is in this place. This one have a discontinuous input current. This one have a continuous input current, and this one idea belongs to Professor Peng and Professor Anderson. Another one is LCCT. This one have a transformator, and this one. The idea in innovator inventor. This one is Professor Strzelecki and Dr. Adamowicz. This one is cascaded quasi-Z source. They have a much more boost factor than another. And this one idea belonged to Dr. Strzelecki. And the last one, switching inductor Z source, this one, the idea belonged to Professor Zuo, Luo, EU. Okay, every structure have another parameters. The most important is boost factor, number of elements, common ground, and that the structure have a continuous input current or discontinuous input current. And the investigation, the whole test performed in the Zephyr chamber according to standards under the supervisor authorized to conduct such research. All tests were carried out of the two loads, 37 ohm and 2000 ohm. Why? Because we don't want to analyze additional influence to, for example, dynamic loads or RL loads. Okay, the analyses which were conducted of disturbance levels and radiation emission began determining the efficiency, the disturbance, changing the modulation dip M without impedance, and we know that changing modulation dip M doesn't matter for this research. This is our device under test. Yeah, I must say that our research as our comparative relative ones, the standards do not specify the recommended methods to compare characteristics. And as we know, in commercial work, only test results is defined. So if somebody have a good one, the system is according the standards. Don't have a problem. If have remarks, must redesign the system. But standards not say how we can compare our results. So the method used to compare the results is based to average of the results of for the entry range, as well as division into comparms and analysis of the record average local maximum value. Okay, what we get, what we have. As we can see, we have lots of results. In our research and our paper, we present only with the worst case. And if we want to focus on these results, we can see that fundamental Z source inverter have the background is higher than, for example, quasi Z source, but it's quite different to analyze. The same situation we have in radiated emission. Only we can see the switching inductance Z source inverter have a much higher results. So in our paper we have a few tables when we have of every results, but it's necessary now it's conclusion. Conducted disturbance. The highest average level of conducted disturbance were obtained for the switched inductance and Z source inverters. The highest average value recorded for the local maximum was determined for the Z source structure. The lowest recorder levels of conductance disturbance were observed to cascade quasi-Z source and LCCT quasi-Z source. And the results of the comparison of the Z source and quasi-Z source using the analysis of the same value should through the Z coefficient present the potential to reduce conducted disturbance during when using a centralized ground as working with continuous input current. Radiated emission, the results discredited the switching inductance Z source inverter structure. The lowest recorded maximum level of radiated emission was obtained for LCCT Z source, quasi-Z source. No significant difference in the levels of interference between structure Z source inverter and quasi-Z source structure were registered as we can see case during the analysis conducted disturbance. The recorder mean level of the quasi-Z source structure was lower in comparison with the level obtained for switching inductance structure. Conclusion: the description of the result will help designer to select the appropriate structure and what structure to choose. Structure with centralized connection to ground, structure with continuous input current, structure with cascade structure, and a structure with smaller switching elements number. Okay, thank you for your attention.
What confuses me, yes, you did not pass the electromagnetic compatibility.
Yeah, yes, yeah, of course.
Did I hear you right that you were using zero voltage switching?
No.
No, it
We
was
only
just
only voltage source. Only we use voltage source inverter with impedance source network. It's normal. No zero voltage switching or no frequency resonance.
Have you analyzed what is the reason of such high emissions?
Yeah.
Have you analyzed the topology or maybe you did some modeling? Where should this noise, electromagnetic interference should be coming from?
Yeah, we have one in this one. Every energy in all structure, the energy is stored in inductance, and we switching this inductance, and as we can see, this one is current choking the inductance. So if we have 1 volt in one step, we have we have 1 ampere in the one step. So 1, 2, 3, 4, 5, 6, 7 ampere, and this is the main reason for this problem we think about.
How was the current measured?
How
did you measure the current?
In
the near field probe?
Yeah.
Okay, thank you.
And how many samples of each structure you tested?
How many?
Samples?
5.
But different 5?
Yeah,
For
yeah.
one structure, one sample?
One sample, 5 different.
But only one sample of
yeah.
each structure?
Yeah.
More questions? Okay, thank you.
Thank you very much.
And the last but not least, I think, presentation will be from Czech Republic. Yeah? The topic is universal pseudo-differential filter using the DCC and DVCCs.
Okay. So, ladies and gentlemen, welcome to my presentation about the research of our group at Czech Republic that we are doing. and dealing with the area of frequency filter design, so a topic very close to Emre, who was giving the speech about all-pass filters. So here in this case about current conveyors, which is the CC standing for. The presentation outline, I will just shortly describe the idea which is behind the description or the labeling of pseudo difference. What does it mean actually, or how at least we understand that. And based on that kind of idea, I will show you and briefly describe a frequency filter that we have designed using this current conveyor, and did also experimental measurements on that kind of circuit and how it works. So from the theory, we should know that we call differential circuits such as that we speak about differential input voltage and differential output voltage. We speak about differential voltage gain, and we expect that next to this mathematical description, we expect that also the inner structure is differential. This is shown simply here on a small, simple RC circuit. So this is what we understand as differential circuit, or also called like true differential, because everything is differential inside. But on the other hand, we can speak also about differential circuits in such a case that yes, we have the differential input and differential output and the differential voltage transfer, because this is only what the math says about differential circuits, and have the inner structure actually single-ended, and at the end result with a more simple structure at the end, because just from this simple circuitry we can see that here we have to use two resistances, and here is only one sufficient. Like the point is that if we would be able from just this simple RC circuit create a differential circuit one, or obtain differential input and output, for sure not. But this is the idea behind of pseudo difference circuits. What we used in our research or in our group, so we are all the, let's say, offsprings of Professor Weber, who was dealing with the area of current conveyors, and we somehow continue in that. And we used in this particular design two types of active elements from this group. One is differential voltage current conveyor, and the second one is differential difference current conveyor. Those who know are very familiar with these equations. Who don't know that, the point is that there are unity transfer voltage and currents between individual terminals, described as shown here. Here we have the final solution, where we can see actually the core of the filter, frequency filter, where you can see that actually yes, it is just a simple structure, single-ended. There is no differential operation observable just from that, but feeding the circuit in appropriate way and obtaining different responses and doing a difference between them, we are able at the end to obtain various transfer functions. In this case, we obtain all the basic 5, so from the high pass to the all pass of the second order, and this is what the theory says, that yes, it should work like that without any problem, and really we can just apply differential voltage here, and from a selected pair of the output nodes we can obtain at the end the required differential voltage response. Above that, what we deal with is the analysis of parasitic properties of the active elements that we use, because they are not ideal, and in this case here we show the influence of parasitic impedances of the input and output terminals, and here we can see that yes, you are just or you cannot stick on the ideal mathematical equation and count the values of passive elements and so on. Just you select few of them. There should be always something behind. And here we see how the transfer function of the high-pass filter here in this example changes the main parameters that we are looking for. So for example, here is the change of the theoretical and true center frequency, and here it's visible the maximum attenuation in the stop band of this high-pass filter, so at the lower frequencies than the center frequency. And so from these plots we can actually provide an convincing fact that yes, what should be the values of passive elements to use for later design. So in this case, like if you would like to obtain the maximum attenuation in stop band, then we would have to go for the highest values of capacitors as possible. But then if we do that, so in that case we are in this corner of the 3D plot. So we will obtain an error in the center frequency, let's say by this 15%. We don't stop at the level of simulations, or not mostly. We try to use the chips that we have of the universal current conveyor, which is able to emulate these types of active elements of the current conveyors that we used in this design. And this is actually the result, and as a hardware. And here we have the result and comparison between simulations and practical measurements, where we know these equations quite well, which describe the ideal behavior, and define, or using them, we can define or determine the values of passive elements in terms of the pole frequency and the polarity factor and so on. And based on that, and using these 3D plots, we can actually say, okay, the most suitable for our case could be the C1 and C2 to have 1 nanofarad, and all the resistors are determined from these equations. And here we can see the expected results. Next to that, which is like a marker, let's say, of these differential circuits. So we describe the common mode rejection ratio. In this case, we obtain for all responses, let's say roughly the 35 dB, that value. If we go for true fully differential, so we have like 80. So there's 50 dB difference. But the only problem in this case, as we can or could observe, is the error between these two voltage transfer to this X terminal. So during the design we can say, okay, once we would go for these structures, so everything can be almost rubbish, but this is the most important part, this section, and that will, if we design this input section very well, then we will reach much higher common mode rejection ratio, even using that kind of simple structure. Then just to sum up, there is the THD of the input signal, and here we should know that the current conveyors are supplied with the voltage plus minus 1.65 volts. So we go, or we are below 1% harmonic distortion with this 1 volt amplitude, so more than 50% of the supply voltage. So to conclude, I was just briefly talking about what's the idea of pseudo-differential filters and how beneficial they could be in terms of true differential systems to provide actually the same features with less complex structure. and we show that not just by simulations but also by experimental measurements. Thank you for your attention.
Thank you. More questions, please? We don't have. Can you open 9th slide?
9?
Yes. Can you
Yes.
explain the difference between this black one?
The black one?
Because most
Yeah.
of them fit.
Yes, yes, yes. So the difference here is caused by the fact that here, when we analyze the non-idle parameters, so here we analyze just the parasitic impedances of the active elements and assume the inner voltage and current transfer to be unity, to be ideal. So this is actually the main problem, because if we would understand also here non-unity, this voltage and current transfer, so this would be huge, and we couldn't be able to analyze it that simple. So this is the main problem, that here we can see that, that we go for 1 nano and 1 nano, and so we should in theory end up somewhere here with the attenuation of somewhere between 60 and 70 dB, but end up later just in theory just below 40. And with these measurements, the second issue is that in these simulations we use the typical parasitic properties of the active element itself, and once we go for the design, then we take a chip and we didn't measure the true values of these parasitics, so we get a bit above, so it's like that.
No questions? Thank you. We finished just in time, and thank you for your attention, for your questions, and now I think you deserve a cup of coffee. Yes?